I'm trying to alternate between videos about math and machine learning and videos about pop culture and regular culture. Today it's more reinforcement learning. You've played Pong, haven't you? It's basically the original video game. It only takes a few seconds to learn how to play, and it only takes a few minutes to get bored and play Skyrim or something instead. But my latest obsession, reinforcement learning, has made Pong a benchmark. OpenAI Gym offers Pong and a whole bunch of other games from the Atari 2600 as environments to play with. If you can program a computer to game as well as, or better than, a human or a squid, you raise interesting questions about intelligence and consciousness. But let's save those questions for the end of the video and play some Pong. The paddle on the left is the original Atari game opponent. The paddle on the right is my computer, which is moving at random. There are 6 possible inputs in Pong, and most of them are repeats. We can press left, right, a different right, fire, or, nope. Left and the different left both move the paddle down. Right and the different right both move the paddle up. Fire and noop both make the paddle do nothing. Every time we give the Pong environment an input, the game advances a few frames with the paddles moving a bit, and we get 4 outputs. First is an observation, a 210 by 160 red, green, blue color image of the game, which we can process into something more computer-friendly. Next is a reward, 1 when we score a point, -1 when the opponent scores a point, or 0 in all the other boring moments. Next is a Boolean true or false, which says whether or not the game is over, which happens when one paddle scores its 21st point. And the last output is how many lives we've got left. The Pong doesn't have any lives, so this one is only cool in other Atari games. With the game over, we reset the environment. This returns the first observation of a new round. I made a neural network which turns the current observation minus the previous observation into inputs which maximize reward. This is called a DQN, a deep Q network. But my first attempt didn't turn out hot. As exploration decreases over time, we see the paddle just gets stuck on one side. The neural network is trying to predict the reward it would get next if it tried each of the 6 possible moves, but it's almost always correct by guessing 0. Adding the next move's reward doesn't help either, because most of the next moves would reward 0 points as well. Producing helpful data is really the big problem in reinforcement learning. Let's look at a version of this which actually works. This article from medium.com describes this code you can check out on GitHub. Links in the description. I hope it's okay for me to describe one person's description of another person's code. If it's not, then medium.com either sue me or hire me. Thank you. The code here is quite interesting to me. The neural network is not written in PyTorch or Keras or TensorFlow. It's written in NumPy. They coded out the backpropagation by hand. And that's not the only difference with my attempt. Their neural network only outputs one number between 0 and 1. It's the estimated probability that the paddle will move up. It's correct about that probability every time, because we take its answer, compare it to a random number between 0 and 1, and if its answer is higher, we make the paddle move up. Otherwise, we make it move down. It's as if exploration is always on. Any move is a coin flip, unless the model says 0 or 100%. How do we train such a model? It's still a DQN, but it looks funky compared to the one I learned last time. Instead of keeping an ongoing memory and picking random batches from it, we just train against all the data from the last game and then delete it. And instead of comparing expected rewards to actual rewards plus expected future rewards, We earnestly compare the expected probability of moving up to whether or not the paddle actually moved up. Huh? But I just explained how expected probability is the actual probability. How could we train this? What is there to improve? And where do the rewards fit in? Right here, in the loss function's weights. Before the pointless training here is applied, it's multiplied by how much we like the results we got. Maybe the model looks at its observations and says its next move would probably be an up, and it happens to be correct. If the reward for this move was positive, we could train it to be more confident about its moving up in situations like that. But if the reward for this move was negative, we can reverse that training. We can tell the model, yeah, you were accurate, and look at what it got you. Better not do that again. So the next time it sees observations like that, it might predict something else. Or maybe the model says it'll probably go up, and at random, it's wrong. It moves down. If it gets a reward, it realizes the direction it wanted to move was a bad one, and it really got lucky moving the other way, so it should do that more often. If it gets a negative reward, it's like saying, yeah, you were totally right, you should have gone the other way. Better bump up the probability on that, so I don't pull the rug out from under you again. And these rewards aren't just 0, 1, or -1. We're spreading the important non-zero rewards into the boring 0 rewards of previous moves by multiplying the reward by some gamma. So in training, the model learns to predict whether or not moving up would be leading to a positive reward or not. When the opponent gets a point, the model considers the bad moves which let that happen. According to the Medium article, training this model to actually play Pong well takes ages longer than any other training I've tried in the past. 3 days before the model can win a game. But I trained the model for 3 days, so let's take a look. Okay, well, now it's time for me to try again on my own. I wrote my own take on this reinforcement learning algorithm in PyTorch. Instead of guessing the probability of moving up, my model guesses 6 probabilities, the probability of each of these 6 moves. It's soft-maxed, so the probabilities are between 0 and 1, and add to 1. The model's move is picked at random from among the 6 moves, but the probabilities are weighted by the model's output. There's no reason to include all 6 moves, since some of them are repeats, but after this I want to try applying the model to other Atari games, and those that have more complicated controls. So let's try it out. I trained for 3 days, and, well, it won't be done training until after I've recorded this script, so let's take a look at it without any comment. Gosh, I hope that was impressive. Whether this worked or not, people have made computers pretty darn good at Pong. This link in the description as well lists a bunch of examples in order of success. A paddle which moves randomly is expected to win an average of maybe about half a point in a whole game. Humans are expected to lose by 3 points, having 18 when the opponent wins 21. But this paper's algorithm tends to win every time without letting the opponent score once. Hot dang. So, is that model a mind? Is there a consciousness in there? Mathematicians often draw a line between neural networks and actual neurons. Even if neural networks were inspired by neurons, and comparing them to neurons is a convenient way to explain them, neural networks aren't really replicating the sodium-potassium pumps which somehow make you you. No matter how good this model can play Pong, playing Pong is a very specific thing to do. This isn't a general intelligence. But when it comes to consciousness, there are 2 kinds of problems. Soft problems are problems science can explain. For instance, we can explain how vibrating air shakes your eardrums, which are wired to your brain. The hard problem is how the brain makes those vibrations into sound which you hear. Like, as a person, how we get qualia, subjective experience. This hard problem, our bizarre awareness of our existence, has led to religions, philosophies, and machine learning algorithms which learn to play Pong. Playing Pong is apparently a soft problem science can explain. When will the soft problems finally stop and we see whatever the heck we actually are deep down? That's all I think about here at Thinkster. One of my inspirations to do whatever I think I'm doing is Code Bullet. He's another YouTuber who made an AI awesome at Snake. If I really think I'm up to it, I might try reinforcement learning on Slither.io. That'd be quite close to the whole predator versus prey scenario I keep talking about. Bye-bye. By the way, I've got a Patreon at patreon.com/thinkster. I want to thank all these squidlings and elder squids. Thanks.